So last time we looked at emission spectra and we looked at how gases absorb certain wavelengths of light and how the absence of certain wavelengths can be an indicator to what gas is present in a star. If there's nothing what's the right word, absorbed, then you would see a continuous spectra. Okay, if you're looking at a white light source in the classroom and that white light source is just set up on the desk and you look at it with a spectrometer, you would see all of the colours present. An emission spectrum is when you have this red to violet. A line spectra is created when certain slices, you could say, or like a barcode are missing. This page is sort of just going over what we'd already done last week. How would you check to see if there's any frequencies or wavelengths missing? Use a spectroscope or a spectrometer. They break the light up into the spectrum for you. Two kinds of spectra, continuous and line spectra. Some sources of light, such as mercury and sodium vapor lamps, do not produce continuous spectrum. These sources contain low pressure gas. The gas glows when you have a high voltage inside the tube. The spectrum that is produced is called a line spectrum, coloured lines spaced out by different amounts. Only specific frequencies are emitted. So those of you that were here, you went next door and you looked through the little spectroscopes at the gas. What you'd have seen would only be different colours. Okay, it might have been red at one end, it might have been purple at the other end, it might have been blue in there. That spectrum that you've seen corresponded to the gas in that lamp. So when you looked at the mercury lamp, you've seen a different spectrum to that of you looked at the neon lamp. So a scientist, you may not have been in, but people did go next door and look through spectroscopes. Scientists may, or was that my fourth year? Okay, I'll double check if we can set it up. It was maybe fourth year. So the colours that you see show you which gas is coming out of the lamp, or the lamp is inside the tube with the gas and the electrons are being created in the tungsten filament. You've done it in fourth year though. You all have had a shot of spectroscopes with your teacher. The little round silver tube with the tiny hole. You look out the back, you see the variable, you see the sort of rainbow colours. Yeah, it's the same experiment as fourth year. So if you were to look and see either the full coloured spectrum with black lines, these black lines would correspond to hydrogen, or if you were to look and see a black background and these were coloured going from the red end to the violet end, you would still know just by the position of the lines where they are on the spectrum what gas you're looking at. Does that make sense? Yeah. So, as with the photoelectric effect, line emission spectra cannot be explained by the wave theory of light. We need to devise some other sort of theory to help us. Now, the only key thing I think we could highlight, maybe I've not highlighted it, is that each element has its own unique spectrum lines, like a barcode. Anybody who's doing chemistry, you'll know a little bit about electron energy levels. So Bohr suggested that electrons occupy discrete energy levels. A free atom is one which is not affected by its neighbouring atoms. So you would have electrons close to the nucleus orbiting, and you'd have electrons at all the different levels, and then you'd have electrons on the outer level. The closer they are to the nucleus, the greater the attraction they have to the nucleus. Because what do we find in the nucleus? Protons, which are positive, and they attract the electrons. So if you're going to move electrons away from this atom, the ones most likely to move are the ones on the outer orbit. If you imagine that on the right hand side we've got this energy diagram, which I'll go into explain a bit more later on in the next page or two, you can then work out where electrons sit in these energy levels and how much energy they have, but I'll add more data to that in a minute. So the outermost electrons are the ones you could remove or make change their energy level. In general, energy levels, the lowest energy level of a system is called its ground state. There's a limited number of energy levels. If the electron moves to a higher energy level, it's in an excited state. It's got lots of energy, it's excited to be where it is. The energies of electrons in various orbits by convention are given negative values. So don't be put off if you see a negative. When an electron moves to a higher energy level, it gains energy and moves to a less negative energy level. So the closer you get to the outside, you are gaining energy and you're becoming less negative. Okay? The attraction to the positive is becoming less because you're getting further away. Energy is needed to free an electron from its atom, we know that. An electron just freed has reached the zero potential energy. When it has escaped the atom, ionization has occurred. In other words, the ionization level is reached when the electron gains enough energy to leave the atom completely. So, a long way of saying you need a lot of energy to leave the atom. When you get to the specific value needed, that's the ionization energy. Here we've got a little example. Electrons can move between energy levels by absorbing or emitting a photon with just the correct energy to match the level. As a result, only certain frequencies of light are emitted, and there's a limited number of possible energy jumps. So our diagram here needs a little bit more written on it. This is a higher level of energy. Here we have a lower level. We don't know if it's a ground state, doesn't tell us. We could call this where it starts, and this is where it's going to jump to. The photon enters this metal surface. The electron absorbs the energy of the photon and it moves to an excited state. It goes to a higher energy level. To work out the energy of the photon, all we have to do is find the difference. Now, we know from earlier on that the energy it has, the change in the energy is equal to HF, the photon energy. Now, if the electron absorbs that, jumps up, and then falls back down from this higher level to the lower level, what happens to the energy it's gained? It turns into kinetic as it moves back down, but it's not given out as heat, it's given out as light. Good. Okay, photon is given out. The energy of the photon given out is equal to E1 take away E0, and we know that's equal to HF. So the frequency of the light given out depends on its energy, because we've got the formula HF. Okay, and for both of these, we just need to remember E equals HF. The energy of the photon is Planck's constant times its frequency. So how do we get different colours of light? It's all based on different energies being given out and absorbed. If I want a high frequency, I will need different amount of energy to a low frequency colour to be emitted, or wavelength. When the electron moves to a high energy level to a low energy level, this is just what we were saying. Energy is released in the form of a photon. And you can think that photon is what we mean by light. The energy of the emitted photon is equal to the difference in the energy between the two levels. Photon energy equals EHF, which is E higher minus E lower. Okay. So I had used the terms E1 and E0. It's just the same thing. This is higher. This is lower. Okay, it goes up because it absorbs the photon, then it goes back down and it gives out a photon. So here we've got electrons falling from a higher level to a lower level, E3 to E2. We've got them falling from E3 to E1. We've got them falling from E3 to E0. If we remember, E equals HF, therefore F equals E over H. The greater the energy, what am I trying to get to the wavelength? Sorry, yeah, the greater the energy, the higher the frequency. And you need to remember lambda equals V over F, and V is constant. Speed of light. So that would be the process you would go through to figure out the wavelength of the light that's being emitted. E equals HF, F equals E over H, Planck's constant, speed of light, photon energy. Step 1, step 2, step 3, you know what wavelength, you could then work out what colour. Most spectra contain bright lines and faint lines. The larger the number of excited electrons that make a transition, so you could have millions of electrons making these transitions at a time, and that colour appears really bright in your vision. Because we just talk about one at a time because that's simplifying it so we can understand the theory. So the more electrons that go up and down energy levels, the more photons are emitted, and the brighter the line in the spectrum. What would I have to do? What would I increase to increase the number of electrons moving up and down if I was shining UV light? What's the word we're looking for? We've just done it in the last 2 periods. I would have to increase something. I would have to increase the something of the UV light. Intensity or irradiance, okay? Increasing the irradiance of light hitting the surface would increase the amount of electrons receiving energy. Would that therefore make the line brighter? How would the wavelength of the photon be calculated? So again, it's just what I've written up here, but we'll write it in here. Step 1, find the photon energy. Which is the higher energy level, subtract the lower. Find the frequency. And that would be through E equals HF. Then you would rearrange that to find F equals E over H. Then you would have to find the wavelength using lambda equals V over F, with V being 3 times 10 to the 8 meters per second. Oops. Too small to be clear. Note, not all electrons produce visible light. Okay? If you fall in a wavelength outside 400 to 700 nanometers, you could be talking about infrared or ultraviolet, which we can't see with our eyes. time is it? So, work to example time. Common type of question this that comes up just on the next page. The diagram below shows some of the energy levels of a mercury atom. Determine the number of possible line spectrums that can be produced by transitions between these energy levels. So, how many jumps can the electrons make? It could go from the fourth to the first. Just ignore the zero just now. Okay, it could go from the fourth to the second. It could go from the fourth to the third. It could go from the third to the first, third to the second. It could go from the second to the first. 1, 2, 3, 4, 5, 6 is the only energy levels we can see there. Now you'll see the energy that the electron has is increasing. Okay, here this is a higher energy. Sorry, I'll zoom in a little bit. And this is a lower, because 2.56 times 10 to the minus 19 is smaller than 16.64 times 10 to the minus 19. 16 is bigger than 2. Remember we said it's only negative because it's an electron. Yeah, we highlighted that previously. So they're given negative signs because they're negative by nature. So calculate the frequency of light that must be absorbed to cause an electron to jump from energy level 1 to energy level 4. So if you're going from 1 to 4, we'll just move down the page a little bit. It's just the difference between them. So we've drawn it as E4 to E1. It's the same energy difference as E1 to E4. Okay, it's a difference between 2.56 times 10 to the minus 19 and 16.64 times 10 to the minus 19. Yeah, 6 is part A, the ones we've drawn up. What is it? 16.64. This is B. Now you can put the negative in if you want because it's an electron. We're just looking for the difference between the two values. The frequency depends on EH over Planck's constant, which is our 14.08 times 10 to the minus 19 joules, divided by 6.63 times 10 to the negative 34. So the frequency of light that must be absorbed to cause an electron to go from 1 to 4 comes out to be 2.12 times 10 to the 15 hertz. Yep. So part C goes on, calculate the wavelength of radiation emitted when an electron moves from level 4 to level 2. So what is the difference in energy between 4 and 2? Delta EK is times 10 to the minus 19 joules. Take away your 2.56 times 10 to the minus 19 joules, which gives you 6.24 times 10 to the minus 19 joules. Again, because it's an electron, it will be a negative sign. We're asked to work out lambda. I'm just going to move this over because the page has run out. Oops, didn't need to change the color of it. So therefore, F equals E over H. 6.24 times 10 to the minus 19 over 6.63 times 10 to the minus 34 comes out to give you frequency 9.41 times 10 to the 14 hertz. Okay, so this value is used here. Then this value is used to help us work out the wavelength. Finally, lambda equals V over F. What's that, sorry? What? Minus 34, yeah. I've lost track. Where am I now? What am I doing? 3 times 10 to the 8 over 9.41 times 10 to the 14 gives you the wavelength 3.19 times 10 to the minus 7 meters, or 319 nanometers. You don't have to put it in that format though. So it's within the visible spectrum, 300 to 400 nanometers. You will get asked to do this probably, these three things. The difficulty is just remembering step 1, step 2, step 3. The actual computation of numbers isn't that tricky, although the numbers are involved in scientific notation. We should be okay with that. Let's take a pause there.